Thank you, everybody, for gracing my talk. As you mentioned, my name is Okwudili Ezeme. I'm a PhD candidate at Ontario Tech University. This is almost the tail of my PhD. It was not intended work, but as all of us know, in research, there are consequences for some of the earlier decisions you make. And this was an outcome for one of them. So everybody is trying to create models to do so many things. As the thrust of my PhD, I was trying to develop anomaly detection using machine learning. And from then, we started moving from the basic statistical approaches using clustering and curve to deep learning. So today, I'm going to explain the background of why we did that. I will give the motivations why we did this particular research, and then I will show the distributed algorithm. I have deliberately skipped some mathematics, but that can be found in poster 51 this afternoon. And then the experiment we did with it, and then the results of and then to show how our hypothesis performed, and then we'll conclude. So in 2010, almost everybody was in the world of security was shocked to discover a computer worm called Stuxnet. It was a worm that was engineered to attack specific device. It was PLC, manufactured by Siemens, using Siemens Step 7 software. And then the Stuxnet one was able to successfully insert itself between the Step 7 software and the PLC. It was able to fool those who were monitoring the nuclear plant because of our outside the zero-day vulnerabilities. It succeeded in fooling them because of the way we program. Almost every of our applications, all the defensive approaches are taken at the application layer. So if somebody successfully puts us in a loop, then we'll continuously be getting feedback that everything is going fine, even though everything is not going fine. So to motivate our research, if we look at all those blocks of code, all of them are applications. If you like, you can call them processes. And a process can have a parent process, and a parent process can have another process. All of them have footprint in the operating system kernel. They are generating events. So if we relied on the return values for monitoring, we can be fooled at that layer. But if we also go down at the operating system and get events being generated, we should be able to know when our system is working fine or not, because you can't hack an operating system while it is working. You have to bring it out, reload whatever you want to do, compile it again, and put it in operation. But before you do that, you'll be caught. So outside the zero-day vulnerabilities, like some of these worms, our defensive programming approach was one of the weaknesses. We only check the values being returned by application or process we are calling. Is it within the range? Is it the same type? And all those kind of things. And then we are also mostly doing anomaly detection at the application layer. So you build a code, somebody asks you to put all the defenses in it, you do that, that's fine. But if somebody with a superior experience comes and hijacks that code, they can successfully fool you. We are not the first people to try to use system calls for anomaly detection. Some people have done that. The only limitation was that they have a kind of graph-based rules that track sequences. So if you want to do online anomaly detection, if you encounter a new state that you have not met before, you have to recompile the graph again. So it is good for mostly offline analysis. And then how about time? So we're now having issues with clock manipulation attack where people can make your code hang for a while. So getting an idea of the next event that is going to happen is not all. You should also know at what time and how long that event is supposed to occur. So that was the motivation of our research. In the process, we built some deep learning models that got from simple to complex because we were trying to get both the quantitative variance, the temporal variance, and the event variance. And then we realized that, okay, if we are concentrating on edge devices or devices performing anomaly detection on the fly, because none of our devices are built for anomaly detection. They actually have some applications they are focusing on. So anomaly detection is like a side action. So it's not giving priority. So in order for us to run, we have to sneak ourselves in by making sure that we maximize all the resources. So that was how we said, okay, this model is getting complex. Is there a way we can break it down and ensure that we can run it in a distributed manner? So that was the idea that came in, and then we said, okay, let's look around. Almost everybody here is subscribed to the Wi-Fi hotspots. So why can't we take advantage of that? It's becoming so common these days. And then some of us have devices that are as powerful as like having 8 gigabytes of RAM, and it could be a handphone cell. But someone like my smartwatch has 4 gig RAM, but all it does is just gives me an event, a notification. So some of these we can take advantage of to make sure that those devices, so far we don't have applications of homogeneous behavior. We don't have devices of homogeneous capacity. We can actually create a subscription-based service where they can use Wi-Fi hotspots to do anomaly processing without resorting to the cloud. So we came up with a data flow model that looks like this. So in our deep learning model, it has 3 main blocks: the feature processor block, the predictor, which is where the deep learning model sits, and then anomaly detector, which uses probability to make decision. Now, we can, using 0MQ, mostly motivated by the fact that with 0MQ, we can have, we don't need to obey the rules of normal circuit programming, which says this guy has to start first and then before this one connects and all those kind of things. Any person can go off and on and come on with and you can come in anytime without following any particular kind of protocol. So everything you see there has been distributed, they are networked with 0MQ. So we can actually do, we are saying wherever the data is generated, we process the features there. So that's the essence of local. For local or peer, it can, anyone that has local or peer means it can be done locally on the device, or it can also go to the peer. And this is the application that sits in the device. So you have the processes coming in. You also have peers sending in, and then whether it can be done locally or it can go to the cloud will be made at that place. Task manager and parameters. What is the role of the Wi-Fi? That's our access point. We also have an application that sits at the Wi-Fi device or router in this place or whichever device you're using. Its role is just to query, to know active nodes and collect their parameters and send. Because if we allow mesh networking, it's going to be messy. So what experiments did we do? We used 10 nodes of different capacity, mostly Raspberry Pis and co. We aimed to determine when we run independently and when we are running distributedly, what is the outcome? So when we say low, moderate, random, and high are referring to the variations in the CPU load, which is how many applications are being monitored. So everything was fine except at the random, where the two results are almost the same, because we discovered that if we allow everything to just run on their own, sometimes almost all our devices can go busty and start emitting devices, in which the decision will say, okay, stay local, and when they stay local, the result is almost as when we didn't distribute. So that will be the thrust of our future work, in which we tend to see what we can do about that. And then, did it affect our normal anomaly prediction? The result, as expected, is no. So using Chebyshev probability. So the details of these are in the paper, which is published at ICML this year. But in the poster 51, I can also give more context if you're interested. So that's all. Thank you.
Hi, thanks so much for giving a talk on this. I find this work kind of really interesting. I work on similar applications, so I'm happy to chat afterwards.
Okay.
I'm interested in sort of knowing a little bit more about the communication aspect of your distributed learning. If you can maybe just explain more on that and sort of what kind of optimization you think could be useful on the communication part.
Okay. So for the communication, like I mentioned, the base library was 0MQ. And then for the considerations, let's say for time, we are basing our latency at most 100 milliseconds. So our assumptions are, so like I said, it was subscription based. So if I'm using this Wi-Fi hotspot in this room as our test center, if you connect and you give permission to join the network, the center, the access point is going to give you all the parameters of all the models that are being monitored in the network. So you have it locally. And then we only have to transfer the input or the output, the results. So we assumed that the value, the size for both going out and coming in, the data size are the same. In actual sense, communication-wise, they are not. But for the sake of the research, we made that assumption. So in this area, I would think of like optimizing the channel bandwidth. Our major challenge was that the bandwidth varied. We thought, okay, Wi-Fi will give us limited stuff, but we realized that as we go towards the edge of the Wi-Fi, what we have in our calculation in terms of the bandwidth was not the same. So I think that's the only area that I think like a communication expert can make more improvement or create a kind of bound mathematically that if you are within this range, this is what you get. Thank you.